Hello viewers, in the series on application of derivatives, today we will discuss increasing and decreasing functions. Have you heard that graphs are faces of functions? Looking at a graph, you can understand what its domain, range and any other characteristic be. Let us see if you can do that today along with me. Starting with this function. In this graph, is it possible for you to say whether this is representing an increasing or a decreasing function without technically knowing what the terms mean? If you observe, as x values are increasing, the values of y are increasing, right? And that is what we mean by an increasing function. If values of y increase as x increases, the function is said to be an increasing function. How about this one? I am sure now you are jumping and saying, yes, I know it is a decreasing function, because as values of x are increasing, values of y are decreasing, and therefore the shape of the graph is letting us know that this is a decreasing function. How about this one? Function partly is increasing, partly it is decreasing, and then again starts increasing. So, over its entire domain, the function is neither increasing nor decreasing. I think you are ready now for the definition which says when do we have an increasing or a decreasing function. So, if I is an open interval contained in the definition of a real valued function f, then f is said to be increasing on I if x1 less than x2 in I implies f of x1 is less than or equal to f of x2 for all x1, x2 belonging to I. This is exactly what you saw earlier as saying that as values of x increase, the values of y also increase. We also distinguish between increasing and strictly increasing with an understanding that if x1 is less than x2 in I implies f of x1 is strictly less than f of x2, then the function is said to be strictly increasing in I. Similar are the definitions for decreasing. X1 less than x2 in I implies f of x1 is greater than equal to f of x2, function is decreasing. Strictly decreasing on I if x1 is less than x2 in I implies f of x1 is greater than f of x2 for all x1, x2 belonging to I. So, what does the derivative have to do with the increasing and decreasing functions? Let us take a minute or two on understanding this again with help of graph of the functions. Here we have graph of a function which over its entire domain is neither increasing nor decreasing, but you do realize with our previous discussion that the blue part is where the function is increasing, the red where it is decreasing. Let us see the relationship of this behavior with the idea of the tangent and derivative. Suppose I take tangent to the curve at any point which is moving around the curve. So, as I drag the point along the curve, the tangent and hence its slope also changes. Can you make an observation on what is happening to the value of the slope? When the point is on the blue part of the curve, the slope is positive. As I come down, the tangent starts rolling down the red part, the slope takes the value which is now negative. Let us see if it changes its behavior again. As I go up this blue curve, it's again become a positive quantity. Further, if I mark the derivative of this function, with this yellow curve, can you see that when the function is an increasing function, that is the part where you see the blue curve, the derivative, the yellow curve, lies above the x-axis, which means f dash x is greater than 0 when the function is increasing. That is what you saw earlier in terms of the slope of the tangent as well. So, slope of the tangent, same as the derivative, is positive when the function is an increasing function. The other part, that is the red part, corresponds to this piece of the derivative which lies below the x-axis. So, when the function is a decreasing function, the derivative is negative, and therefore, that part of the graph lies below the x-axis. If I mark the intervals in which this behavior is observed, then all the values from minus infinity to minus 4 are the values, the subinterval of the domain over which the function is increasing, and on the other side, starting from 3 towards infinity, all values gives rise to increasing behavior of the function. Whereas, between this minus 4 and 3, I get the segment which represents the interval over which the function is a decreasing function. So, what you saw just now connects the conditions of derivative with the behavior of a function as an increasing and a decreasing function. Put together, here is a theorem which states just the same. Let f be continuous on closed interval a b and differentiable on open interval a b, then f is increasing in closed interval a b if f dash x is strictly greater than 0 for each x belonging to a b. F is decreasing in closed interval a b if f dash x is less than 0 for each x in this open interval. So, what you saw just now in a dynamic way put together results in a theorem which works as a condition to test whether a function is increasing or decreasing. What the theorem says is, let f be continuous on closed interval a b and differentiable on open interval a b. Then f is increasing in closed interval a b if f dash x is greater than 0 for each x belonging to a b interval, and f is decreasing in closed interval a b if the derivative takes values less than 0 for each x belonging to open interval a b. That is exactly what you saw just now. And f becomes a constant function if derivative takes the value 0 for each x belonging to open interval a b. So, no change happens, and therefore, it is going to be a constant function. Let us see if we can apply this theorem to figure out whether a given function is increasing in the mentioned interval. The problem says show that f of x is equal to 1 minus cos x is an increasing function for all x belonging to the real numbers. Starting with the derivative, which is 1 minus cos x, that is same as writing 2 sin square x by 2 using the basic identity from the trigonometry. This expression is always greater than or equal to 0 being the square, and therefore, the function is increasing. Alternately, you can also say that 1 minus cos of x is greater than equal to 0 because cos x takes the values between minus 1 and 1, ends included, and therefore, this function, that is f dash x, is always greater than equal to 0, and therefore, the function f is an increasing function for x belonging to real numbers. Let us take another question where we have to find the intervals over which the function increases and decreases. The problem states, determine the intervals where f of x equal to sin x minus cos x between the interval 0 to 2 pi is strictly increasing or strictly decreasing. Of course, the work starts always with f dash x. I have to figure out the values of x for which f dash x is greater than 0, and to do that the best would be if I can put them together as a single trigonometric function, and to do that I multiply and divide by root 2, which helps me to rewrite this as root 2 times of sin x plus pi by 4, because 1 by root 2 cos x plus 1 by root 2 sin x is same as either using sin pi by 4 as 1 by root 2 in the first place or in the second. The expression simplifies to sin a cos b plus cos a sin b or cos a cos b plus sin a sin b. I have chosen to write the 1 by root 2 cos x as sin pi by 4 cos x and the other term as sin x into cos pi by 4. So that the f dash x becomes root 2 times of sin of x plus pi by 4. Now, f dash x will be greater than 0 if sin of x plus pi by 4 is greater than 0, which means I need a condition on x plus pi by 4 from here. Sin theta is positive if theta lies in the first and second quadrant. So, x plus pi by 4 must be between 0 and pi, which gives me a condition on x as between minus pi by 4 to 3 pi by 4. But we have an understanding that the domain of the function was 0 to 2 pi. So, this condition splits into two intervals, 7 pi by 4 to 2 pi or 0 to 3 pi by 4. Therefore, f dash x is greater than 0 when x belongs to 0 to 3 pi by 4 or 7 pi by 4 to 2 pi, and therefore, f is strictly increasing in the interval 0 to 3 pi by 4 and 7 pi by 4 to 2 pi. Similarly, you can discuss the behavior of f dash x less than 0 and find the conditions on x. So, sin theta is negative when theta lies in third and fourth quadrant. So, x plus pi by 4 lies between pi and 2 pi, giving rise to x between 3 pi by 4 and 7 pi by 4, and therefore, f is strictly decreasing on 3 pi by 4 to 7 pi by 4. And since, as I said earlier, graphs are phases of functions, this is what the graph of sin x minus cos x looks like, and it does confirm the answer that we have evaluated in this discussion. So, knowing the conditions under which a function is increasing and decreasing, we have covered two possibilities: verify whether the function is increasing, decreasing, and we have discussed how to find intervals over which a function is increasing and decreasing. Hope you have enjoyed today's lesson. Best of luck, and we will meet again. Thank you.